Our next section is 12.3, Calculus and Polar Coordinates. Having learned about the geometry of polar coordinates, we now have the tools needed to explore calculus in polar coordinates. Familiar topics such as slopes of tangent lines, areas bounded by curves, and arc length are now revisited in a different setting. This can be a little confusing, as given a function y equals f of x, the slope of the tangent line to the graph at a given point is dy dx, or f prime. So it is tempting to conclude that the slope of a curve described by the polar equation r equals f of 0, where you think of r as the x value and f of 0 is the y, f of theta, not f of 0, excuse me, is the y value. It's tempting to think of dr d theta, which would equal the derivative of f of theta. Unfortunately, it's not that simple. The key observation is that the slope of a tangent line in any coordinate system is the rate of change of the vertical coordinate with respect to the horizontal coordinate x, which is dy dx. So we really have to translate the polar equations, r equals f of theta, in parametric form with theta as a parameter. So here we have x equals r cosine theta. Substituting in f of theta for r, we get x equals f of theta cosine theta, and similarly we get y equals f of theta sine theta. From our first section in chapter 12, when x and y are defined parametrically as differentiable functions of theta, then the derivative becomes dy dx, which is dy d theta over dx d theta, taking each individually. Using the product rule, dy d theta and dx d theta in equation 1, we now have a product rule in the numerator and a product rule in the denominator. So dy dx becomes f prime theta sine theta plus f of theta cosine theta. And the denominator becomes f prime theta cosine theta minus f sine of theta, okay? Again, thinking about what each one is, r cosine theta would be f of theta cosine theta. So the derivative of the first, I'm just going to do the denominator here, is the f prime theta cosine theta, and then f of theta times the derivative of cosine theta, which is negative sine theta, and that's how you get the denominator. And similarly, the numerator. If a graph passes through the origin for some angle theta sub 0, then the y value of that polar coordinate f of theta sub 0 is going to also be equal to 0. And equation 2 simplifies into dy dx equals sine over cosine at theta sub 0, which of course is equal to tangent of theta sub 0. Provided that the derivative of theta sub 0 doesn't equal 0. Assuming cosine theta sub 0 does not equal 0, then the tangent of theta 0 is the slope of the line theta equals theta sub 0, which also passes through the origin. In this case, we conclude that if f of theta sub n equals 0, then the tangent line at 0, theta sub 0, is simply theta equals theta sub 0, which you can see in the figure to the right. If f of theta sub 0 does in fact equal 0, then the derivative does not equal 0, and cosine theta equals 0, which means that the derivative is undefined, and we know that an undefined derivative is the slope of a vertical line. So we'd have a vertical tangent line at the origin. So here's theorem 12.2, the slope of a tangent line. Let f be a differentiable function at theta sub 0. The slope of the line tangent to the curve r equals f of theta at the point f of theta sub 0. Theta sub 0 is dy dx, which is the derivative of f of theta sub 0 times sine theta plus f of theta sub 0 times the cosine of theta, all divided by f prime theta sub 0 cosine theta sub 0 minus f theta sub 0 sine theta sub 0. And this is what we just walked through in the last slide. And that's provided the denominator is non-zero at the point. At angles theta sub 0, for which f of theta sub 0 equals 0, and f prime doesn't equal 0, and cosine theta sub 0 doesn't equal 0, the tangent line is theta equals theta sub 0 with the slope tangent of theta sub 0. That's just kind of combining all the thoughts that we had before on the previous slide and above. So let's see how that theorem plays out as we try example number 1, slopes on a circle. Find the slopes of the lines tangent to the circle r equals f of theta, which equals 10. Well, the first thing we notice is that r is now a constant. It's not dependent upon different values of theta. So that implies that the derivative of f of theta is going to be equal to 0 because it's the derivative of a constant. And what that means is both of these first terms will cancel out because f prime theta, the derivative of a constant, is 0. And so we're left with 10 cosine theta over negative 10 sine theta. The 10s cancel out and we're just left with negative cosine theta over sine theta, which of course is negative cotangent theta. We can check a few points to see that this result makes sense. With theta equals 0 and theta equal pi, the slope dy dx is undefined, which implies that the vertical lines, the tangent lines, are vertical at these points, which we can see here and here. So that does play out. With theta equals 3/4 pi and theta equals 7/4 pi, 7/4 pi, the slope is 1. And with theta equal pi over 4 and 5 pi over 4, the slope is negative 1, again, which we can kind of see handling here. And we can do that just by plugging in those values or taking the cotangent at those specific points. All right. Therefore, OP is perpendicular to the tangent line at all the points on the circle. For example 2, we're going to look at vertical and horizontal tangents. Remember that vertical tangents occur when the derivative is undefined, and horizontal tangents occur when the derivative is 0. Find the points on the interval negative pi is less than or equal to theta is less than or equal to pi. Okay, so we're talking about that's interesting. We're talking about the whole 4 quadrants, but they've defined it around the origin, which is interesting. And that's fine, but notice negative pi would be negative 180, and pi, of course, is positive 180. So we are still looking at all 4 quadrants, at which the cardioid r equals f of theta is equal to 1 minus cosine theta, and it's specifically we're trying to find the points where it has a vertical or horizontal tangent line. So applying the theorem from 12.2, remember the derivative is f prime theta sine theta plus f of theta cosine theta, f prime theta cosine theta minus f of theta sine theta. We have f of theta here given to us in the problem. It's easy to take the derivative. The derivative of cosine is negative sine, and so we get 0 minus negative sine, which is positive sine. So now we can plug in the f of theta value and the f prime value, which is what we've done here. So we have sine theta plus 1 minus cosine theta, excuse me, times sine theta cosine theta minus 1 minus cosine theta sine theta. Okay. Well, sine theta squared, sine squared theta, is equal to 1 minus cosine squared theta. So we're going to plug that in, multiply this through. We get plus cosine theta minus cosine squared theta. Okay. When we combine 1 minus cosine squared theta with cosine theta minus cosine squared theta, we get negative, and pulling the negative out in front, 2 cosine squared theta minus cosine theta minus 1. In the denominator, if we factor out a sine theta from both of these values, we get sine theta times cosine plus cosine is 2 cosine theta minus 1. Okay, so we get this version here. If we factor the numerator, we get 2 cosine theta plus 1 times the quantity of cosine theta minus 1 all over sine theta times 2 cosine theta minus 1. Now, why are we going through all these steps? We're trying to find out the derivative. And remember, we're looking for vertical and horizontal tangents. Okay, vertical tangents occur where the derivative is undefined, or since we have a rational expression, where the denominator is 0. So we're going to look for the values of theta where sine of theta is 0. We're also going to be looking for values of theta where 2 cosine theta minus 1 equals 0. Horizontal tangent lines occur when the derivative is 0, and when you have a fraction is 0 when the numerator is 0. So the numerator gives us, the numerator being 0 gives us horizontal, the denominator gives us, when it's 0, gives us the vertical tangents. And that's what that's saying there. So notice that the numerator is 0. So we have cosine theta minus 1 equals 0. Well, that means cosine theta equals 1. Well, cosine theta equals 1 when theta equals 0. 2 cosine theta plus 1 equals 0 when cosine theta equals negative 1/2, which would mean we're in quadrant 2 or in quadrant 3, right? Cosine is negative in those quadrants, and specifically cosine theta equals negative 1/2 at 2 pi over 3, and at negative 2 pi over 3. 2 pi over 3 is 120 degrees, and that's stretching back to your trigonometry knowledge, building those triangles, the 30, 60, 90 triangle, and so 120 is we can use the 60-degree reference angle to find those. So we have 3 values for when the numerator is 0. Okay? Because the denominator is not 0, if we plug in 0 into the theta equals 0 into the denominator, right? Well, the sign of 0 is 0, and so that's a problem. Okay? So we can't use this value because instead of just having 0 in the numerator, again, when we plug theta equals 0, sine theta becomes 0, and we have 0 over 0, which kind of eliminates this as a vertical tangent line, at least for now. Okay, so we have 2 values, plus or minus 2 pi over 3, theta equal to plus or minus 2 pi over 3, and we had to define it this way instead of, because of the interval we're given. Instead of between 0 and 2 pi, we were given negative pi and pi, so we have to calculate the angles in a counterclockwise for the positive and a counterclockwise for the negative. The clockwise for the negative is quadrants 4 and quadrants 3. Okay. So now we can do the denominator. We've already seen that the denominator equals 0 when theta equals 0, but the numerator does as well, so there's a conflict there. 2 cosine theta minus 1 equals 0 when cosine theta equals 1/2, positive 1/2. This occurs in the first quadrant and also in the fourth quadrant at pi over 3 or 60 degrees from that same known triangle and same known angle in trigonometry. Okay, so we have vertical tangent lines at at plus or minus 2 pi over 3, 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 plus or minus 2 Let me restate that. So we have horizontal tangent lines at plus or minus 2 pi over 3. We have vertical tangent lines at plus or minus pi, because this is when at 0, also remember that sine of theta is 0 when theta is pi. That's the y value. So pi, plus or minus pi are also two values for the denominator to be 0. So we have vertical tangent lines at plus or minus pi, and then plus or minus 60 degrees, or pi over 3. We still have that condition where we have 0 over 0. Both the numerator and denominator are equaling 0 when theta equals 0. So that's something else we have to kind of figure out. And here is the graph that we're seeing there. The point 0, 0 on the curve has to be handled differently, because both the numerator and denominator of the derivative go to 0, as we just walked through. But what we can do, since both the numerator and denominator go to 0, is apply the limit as theta goes to 0 to see what's happening as we're getting closer and closer to 0. Because both the numerator and denominator go to 0, as theta goes to 0 from the positive direction, we can apply L'Hopital's rule. And so when we do that, we get, finally, I'm not going to walk through this, but we get 0 over 1, which equals 0. So this rule shows that as theta goes to 0 from the negative direction, it also goes to 0. Therefore, the curve has a slope of 0 at 0, 0, which means that effectively it is indeed a horizontal tangent line. So it would be included in the horizontal tangent lines versus the vertical. Next, we're going to look at areas of regions bounded by polar curves. The problem of finding the area of a region bounded by a polar curve brings us back to the slice and sum strategy used extensively in chapters 5 and 6 that we learned first in Calculus 1. The objective is to find the area of the region R, bounded by the graph of R equals f of theta between the rays theta equals alpha and theta equals beta, as you can see in the top graph to the right here. We assume the function is continuous and non-negative on alpha-beta interval. The area of the region is found by slicing the region in a radial direction, creating wedge-shaped slices. The interval alpha-beta is partitioned into subintervals by choosing the grid points alpha equals theta sub 0, which is less than theta sub 1, which is less than theta sub 2, as you can see here as well. We let delta theta sub k equal theta sub k minus theta sub k minus 1 for k equals 1, 2, all the way up to the n number of regions that we've created. And we let theta star sub k be any point on the interval between theta sub k minus 1, theta sub k. This gives us a k slice. The k slice is approximated by the sector of a circle swept out by an angle of delta theta k with the radius of f of theta sub k. This is, again, the idea of choosing any point within an interval of a slice. And you can see that here with this one slice being defined for delta theta sub k. Therefore, the area of the kth slice is approximately 1/2 f of theta sub k squared times delta theta sub k. Okay, to find the approximate area of that region R, we sum all of the slices, and so we get the area equals the summation from k equals 1 to n of 1/2 f of theta star sub k squared times delta theta sub k. The approximation we just came up with is a Riemann sum, and the approximation improves as we take more sectors, or specifically as n goes to infinity, and let delta theta sub k go to 0 for all k. The exact area is given by the sum, the limit of the sum, as n goes to infinity from k equals 1 to n of 1/2 f of theta sub k star squared times delta theta sub k, which we identify as the definite integral between alpha and beta of 1/2 f of theta squared d theta. With a slight modification, a more general result is obtained for the area of the region R bounded by two curves, R equals f of theta and R equals g of theta, which you can see in the diagram to the right. Again, we're still using the same interval between theta equals alpha and theta equals beta on this diagram. We assume that f and g are continuous and that f of theta is greater than or equal to g of theta, which is greater than or equal to 0, so they're all positive on that interval. To find the area of that region, R, that we see in the diagram, we subtract the area of the region bounded by R of g theta, which is below, from the area of the entire region bounded by R equals f of theta. Again, this is all from Calculus 1, the upper curve minus the lower curve. So in this case, we get the area is equal to the upper curve integral minus the lower curve integral, which specifically just gives us the integral from alpha to beta of 1/2 f of theta squared minus g of theta squared d theta. Okay? Which leads us to the area of regions in polar coordinates. If we're just looking for the area under a region and not between curves, notice the second function goes away, g of theta squared. And so you can read through this definition, but this gives us a general form. And then of course, again, if we're not looking for the area between curves, the second function goes away. So we're a little less than halfway through this lecture, and it is an hour-long lecture. So I think it's a good idea to go ahead and take a break at this point. We've learned some concepts that we're about to do some examples for, so you may want to do the next two examples and then take a break, but this was the more natural spacing and timing for a break. So you choose, either break now or break after the next two examples. So let's try our next problem, the area of a polar region. Find the area of the four-leaf rows, R equals f of theta, which equals 2 cosine 2 theta. Here we have the formula from the general definition, the generalized formula, and notice g of theta squared is not going to be used because we're only looking for the region underneath one curve. Here we see the graph of the diagram of 2 cosine 2 theta. And notice the graph of the rows appears to be symmetric around the x and y axis. In fact, these symmetries can be approved. Appealing to the symmetry, we find the area of 1/2 of a leaf. Now, why did we do 1/2 of a leaf? Well, we're looking for all values that are above the x-axis or all regions that are positive. If we can find the region above the x-axis, multiply that by 8, then we will have the total region bounded by this curve. Okay, so we can see that the upper half of the rightmost leaf is generated as theta increases from 0 to pi over 4. Therefore, the area of the entire rows is 8 times the integral from 0 to pi over 4 of 1/2 f of theta squared d theta. So now simply plugging in this into our formula, f of theta is 2 cosine 2 theta squared. So we get the cosine squared. Again, we can take out, first we multiplied 8.5 because we can take out any constants outside of the integral, and we got 4. Well, here we're going to get 4 cosine squared 2 theta, and then we can take that 4 out. 4 times 4 is 16. So what we're doing is we're evaluating the integral from 0 to pi over 4 of cosine squared 2 theta d theta times the multiplier of 16. Here we've substituted in the half angle formula from trigonometry, 1 plus cosine 4 theta over 2. So notice what this gives us is the integral from 1/2 plus the integral of 1/2 cosine 4 theta. So the integral of 1/2 is 1/2 theta, and 1/2 theta times 16 is 8 theta. The integral of cosine 4 theta, 1/2 cosine 4 theta, 1/2 cosine 4 theta. The integral of cosine is sine, and then of course this is a composite function, so 4 theta, the derivative of that is 4, so we'd pull that out and make sure it's in there, and so we end up with a multiplier of 1/2 times 4, which is 2, or 1/2 of that in the denominator, so we're going to end up with 2 sine 4 theta. I feel like I didn't explain that very well. When we get here and we divide this into two fractions, 1/2 plus 1/2 cosine 4 theta, when we're doing the second half, we get 16 times 1/2, which is 8 on the outside of the second integral. So we're taking the integral of 8 times the integral of cosine 4 theta. Well, here we have to do a substitution. We make u equal 4 theta, and so du would equal 4. Well, if we add 4 inside, we have to divide that 8 by the 4 on the outside, and so the multiplier becomes 2 here. Therefore, we can now see that our whole integral value is 8 theta plus 2 sine 4 theta between 0 and pi over 4, which gives us 2 pi plus 0, 8 times 4 pi over 4, and 8 times 0, minus 2 times the sine of 4 theta. When theta is pi over 4, we get the sine of pi, which is 0, and of course the sine of 0 is 0. So in the whole values, we get 2 pi for this region. So now let's look at another example about how to calculate areas of polar regions. Consider the circle r equals 1, which you can see here to the right, and the cardioid r equals 1 plus cosine theta, which you see here, this kind of sideways heart shape. For part A, find the area of the region inside the circle and inside the cardioid. Okay, so in this green figure, you can see that shape is already shaded. It's inside the circle and inside the cardioid. So we can see that the shapes, the shaded area, the region that we're trying to calculate the area of, is a half a circle. And then it's got these two little semicircles or half moons or part of a moon, whatever you want to say, on the left side of the y-axis. Now, whenever we're trying to figure out the area between two curves that's bounded by curves, we have to figure out first what are their intersection points, and we can see that sort of here. So the first thing we need to do is to find the points of intersection. And while we can see that graphically here, we really want to solve it analytically as well. And so we want to set the two equations equal to each other. R equals 1 plus cosine theta equals 1. Okay? So when we set these two equations equal to each other, 1 plus cosine theta equals 1, we get cosine theta equals 0. And of course, cosine equals 0 at pi over 2 or 90 degrees, and also at 3 pi over 2, which I believe we're using negative instead of the full revolution. So we'd have intersections at pi over 2 and negative pi over 2. Okay? Well, since we know that the radius of a circle is 1, and we know that the area of a circle is pi r squared, which would just be, since r is equal to 1, we'd have pi times 1 squared, which would be just pi. So the entire area of the circle is pi, but the shaded area only has half of that circle. So we already know the area of the semicircle, which would be pi over 2, half of the circle, okay? And that's what this says here. The other thing we can see is that we have two of these identical shapes in these little half moons, or whatever you want to call them, okay? So if we figure out the area of the shape above the x-axis, we can multiply that by 2 to figure out what the area of those two little bumps on the edge are, okay? Now, when we're trying to find the area between two curves, we take the outer curve minus the inner curve. And remember, the outer curve is simply 1, and then the inner curve is 1 plus cosine theta, okay? So we get the and the limits, the alpha and the beta, are going to be pi over 2 to pi, because we're just doing this second quadrant shape here. So we get the integral from pi over 2 to pi of 1/2 1 plus cosine squared d theta. Now that I look at this, it's not the area between these two curves, because that would be the area inside the circle and outside the cardioid. What we have here is the shape between the cardioid, 1 plus cosine theta, and the y-axis, which would be just 0. So we're really just looking for this little, again, half moon shape between pi over 2 and pi. We're not subtracting the two graphs. I made a mistake there. If we were subtracting those two graphs, notice we'd have the shaded area inside the circle and outside those little half moons. All right, and that's why we have this. So we have the integral from pi over 2 to pi of 1/2 times 1 plus cosine squared, which gives us, if we square that, we get pi over 2 to pi of 1/2 times 1 plus 2 cosine theta plus cosine squared d theta. So pulling the 1/2 outside, and changing cosine squared into 1 plus cos 2 theta over 2, which is the half angle formula, we can then take the integral of each piece, the integral of 1 being theta, the integral of 2 cosine theta being 2 sine theta, the integral of 1/2 being theta over 2, or 1/2 theta, and the integral of 1/2 cosine 2 theta is sine 2 theta over 4, as we saw in the previous example. When we plug in the values of theta between pi over 2 and pi, and plug in those values, we get 3 pi over 8 minus 1. Now that's just the area of the top shape, so we have to multiply that by 2, ultimately getting 5 pi over 4 minus 2. So I kind of took you on a few wrong turns here, but I didn't re-record the video because I think it's these are good mistakes for you to see me make, so that you're paying really close attention and thinking about the graph and what area you're trying to calculate the area of. So now let's look at B. Find the area of the region inside the circle and outside the cardioid. And that's here. And this is the mistake I made before that's more accurate here. So we can see the shape again is the same above and below the x-axis. So if we just calculate the area above the x-axis from pi over 2 to pi, then we can multiply that by 2 to get the total area. Now in this case, what we want is the area between the two graphs. So in this case, we're going to have the graph from 1, r equals 1, to r equals 1 plus cosine theta. So the integral from pi over 2 to pi of 1 minus 1 plus cosine theta. Okay? So again, we're going to have 1/2 that area, which is 1 squared minus 1 plus cosine theta squared. 1/2 times that, 1/2 times f of theta squared. And then we're going to double that so that we count above and below the axis. Okay? This simplifies into negative 2 cosine theta minus cosine squared theta, which simplifies once we take the integrals there into 2 minus pi over 4. Note that the regions in part A and B make up the interior of a circle of radius 1. Indeed, their areas have a sum of pi, because here we had this side of the circle and now we have the other side. So together they would add up to pi, which is another good check that we could have here. Sometimes it's really difficult to find the points of intersection, so we're going to look at a problem specifically focused on this, about finding the points of intersection of the circle r equals 3 cosine theta and the cardioid r equals 1 plus cosine theta, which you can see here in the diagram. So we're looking for the points of intersection. The fact that a point has multiple representations in polar coordinates may lead to subtle difficulties in finding the intersection points. We first proceed algebraically, equating the two expressions for r and solving for theta. So we set 3 cosine theta equal to 1 plus cosine theta and solve for cosine theta. This gives us theta roots of plus or minus pi over 3. Therefore, the two intersection points are 3/2 pi over 3 and 3/2 negative pi over 3, which you can see on both diagrams. Yet when we look at the figure, we can see that there's another intersection point at the origin that has not been detected. To find this intersection point, we must investigate the way in which two curves are generated. As theta increases from 0 to 2 pi, the cardioid is generated counterclockwise, as you can see in the arrows here, beginning at 2, 0. The cardioid passes through the origin when theta equals pi, and as theta increases from 0 to pi, the circle is generated counterclockwise as well, beginning at 3, 0. The circle passes through 0 when theta equals pi over 2. Therefore, the intersection point is 0, pi. On the cardioid, and unfortunately these coordinates do not satisfy the equation of the circle, while the origin point O is 0, pi over 2 for the circle, and these coordinates don't satisfy the equation of the cardioid. There is no way to foolproof way of detecting these hidden intersection points, so you have to really be really careful, and we'll look at this. I think we're going to continue this problem in example 6. So now let's look at that same shape and compute 3 different areas from example 5. Example 5 discussed the points of intersection on the curves r equals 3 cosine theta, which is a circle, and r equals 1 plus cosine theta, which is a cardioid. Use these results to compute the areas of the following non-overlapping regions in figure 1242. Okay? So when we look at figure A, we can see that we're going from theta equals 0 to theta equals pi over 3. And here we have the circle, which is 3 cosine theta, minus the cardioid, which is 1 plus cosine theta, and again evaluated from 0 to pi over 3. Therefore, the area of the region is 1/2 the outer function squared minus the inner function squared at theta. The outer function again is 3 cosine theta, and the inner function is 1 plus cosine theta. Okay, and of course, using our formula from the theorem, we square each of those f of thetas. Okay. I'm not going to walk through this integration solution. You should be able to do this now, especially using the double angle substitution. We've seen that a couple times in this section and chapter, and you should be able to walk through this. And so ultimately we get pi over 2. What I'm really concerned about is making sure you understand this formula, highlighted in yellow at the top, and then you can figure out, based upon intersection points or graphs or shaded areas, how to find this integral and define the limits alpha and beta and each of the functions. Okay? So notice if we look at figure B, area B, I should say, region B, notice we sort of have two different shapes. It's kind of a little confusing, right? So from 0, theta equals 0 to theta equals pi over 3, notice this is the shape of the cardioid. There's no lower boundary. There's not a function beneath this, okay? And so, and then when we get on the other side of that, from theta equals pi over 3 back to the origin, notice all we have here is the circle function with no other curve underneath it. So both of these calculations, you can see this line kind of splitting those regions, both of those calculations have no lower bounds. Neither of them have a g of theta from the formula. Okay? So again, if we draw a ray kind of between the origin and this point, you can see that we're actually calculating two areas. One under the cardioid from, again, 0 to pi over 3, this intersection point. And again, it's 1/2 times f of theta squared. And the cardioid is 1 plus cosine theta squared. And then we also have this other area under the circle, and this is from pi over 3 to the intersection point of the circle at the origin. And so remember that the circle intersected the origin at theta equals pi over 2. So we are calculating from pi over 3 to the circle's intersection point, pi over 2, and then of course using our formula 1/2 f of theta squared, and the circle is 3 cosine theta. So again, we've got an area, some suggestions here that we can evaluate the integrals. It's saying that the area of region B equals the area of the semicircle OPQ. So that's OP, where's Q on here? The region of A. Oh, I see what it's doing. It's doing the semicircle OPQ. So this is a circle of radius 3, right? So that's pi r squared, so 9 pi. And then subtracting out the area A that we just saw before. Okay? Boop, boop, ba-doop, boo. So it's giving you a kind of a geometric way to calculate the area instead of using the integrals here. And I just misspoke because r equals 3 cosine theta. I was looking at this and thinking this was the radius 3, which I misspoke. Notice this is the diameter from 0 to 3. So the radius of 3 cosine theta is actually 3 divided by 2, which is 3/2, which they've got it correctly here, 1/2 pi r squared. Okay. All right. So this one we didn't even have to do the integrals, but being able to set them up is very helpful. And I didn't, even when I was doing this problem, I actually solved the integrals. I didn't notice that we could take the semicircle and subtract out a that we had already calculated in part A. So those clever guys even pulled one over on me. So now let's look at the last part, C. And that's this kind of, not a half moon, but a piece of a moon slab there that you see. Okay. So we have to be careful here because it, if we look at this, it looks as though this is the cardioid minus, I just went blank there, sorry, the circle, right? Because we're talking about this little shape here. So it's easy to incorrectly identify the inner boundary of region C as the circle and the outer boundary as the cardioid. While this is true from pi over 3, theta equals pi over 3 to the y-axis where the cardioid intersects at pi over 2, so from pi over 3 to pi over 2, that is correct. It's the upper curve minus the lower curve. But as soon as we cross over into quadrant 2, notice there is no lower boundary curve. It's just the curve of the cardioid from pi over 2 to the cardioid's intersection point at the origin. So here we would just have no lower bounds. We just have the integral of the cardioid, okay? And so we see here again, we have an integral from pi over 3 to pi over 2. That's from this point P to the y-axis, and it's the upper curve, the cardioid, minus the circle, which is what you have here. Plus this other area in quadrant 2, which doesn't have any lower boundary, it's just between the axis points. So it's the cardioid, it's just the integral of the cardioid from theta equals pi over 2, again, to the origin point, which remember the cardioid theta value for the origin was pi. And here they've calculated the area for you, and I'm not going to go through those steps for calculating that, but it might be a good idea for you to make sure that you get pi over 8 when you solve this, I'm sorry, I went blank, integrals. So our last piece of content for this section is determining arc lengths of a polar curve. We now answer the arc length question for polar curves. Given the polar equation r equals f of theta, what is the length of the corresponding curve for theta between alpha and beta, assuming the curve does not retrace itself on this interval? The key idea is to express the polar equation as a set of parametric equations in Cartesian coordinates, and then use the arc length formula for parametric equations derived in 12.1, letting theta play the role of the parameter and using r equals f of theta. Okay? Parametric equations for the polar curve are, remember, x equals r cosine theta, or f of theta cosine theta, and y equals r sine theta, f of theta sine theta. And if we're looking at theta between alpha and beta, the arc length formula in terms of the parameter theta is the integral between alpha and beta of the square root of the derivative of x with respect to theta squared plus the derivative of y with respect to theta squared. Now, if we take the derivative of x with respect to theta, f theta cosine theta. Again, using the product rule, we get f prime cosine theta minus f of theta sine theta. If we do the same thing with y equals f of theta sine theta, using the product rule, we get dy d theta equals f prime sine theta plus f of theta cosine theta. Okay. Now remember, we're squaring each of these, so we have a FOIL or a binomial squared right here and here as well, and then simplifying that. And when we simplify that, what we end up with is this simplified formula, because all the other terms cancel as far as the cosine and sine, or the cosine squared plus sine squared equals 1, etc. So the arc length of the polar curve r equals f of theta on alpha beta is simply the integral from alpha to beta of the square root of f of theta squared plus the derivative of f of theta squared. So this is a greatly abbreviated formula that we can then use in the next example. So let's look at our last example in this section, finding arc lengths of polar curves. Part A, find the arc length of the spiral r equals f of theta equals theta for theta between 0 and 2 pi. So here's the diagram of that we've seen this formula before, r equals f of theta equals theta. So as theta increasing, r is increasing, and so we have this kind of outwardly going spiral. Here we have the arc length formula. Right, so we have f of theta squared. Well, f of theta is just theta. F prime of theta is simply 1, right? Like the derivative of x is 1, so the derivative of theta would be 1 as well. So we have theta squared plus 1 squared, and here we're evaluating it between 0 and 2 pi, and so that's what you see here in our calculation. When we look for this integration of the square root of x squared plus 1, if you look in your table of integrals, specifically number 76 in your book, you will find that the integral of the square root of x squared plus 1 equals 1/2 x, or x over 2, times the square root of this x squared plus 1 plus a over 2, this being a, the constant over 2 times the natural log of the x plus the square root of x squared plus a. And so we can substitute this in and then just do the calculation by plugging in the values between 0 and 2 pi, and then using our calculator to calculate the value, and we end up with 21.26. For part B, we're finding the arc length of the cardioid 1 plus cosine theta. So f of theta equals 1 plus cosine theta, so it's going to be the square root of 1 plus cosine theta squared plus the derivative squared, right? Well, the derivative of 1 is 0, and the derivative of cosine theta is negative sine theta. So we'd have negative sine theta squared. So here we have 1 plus cosine squared, and here we have negative sine theta squared. Okay, and you can see those two values there, and then here is a diagram or graph of this function. So plugging that in, notice what we're going to do here. We're going to calculate, oh no, the arc length, my bad. Let me ignore that. So we're going to calculate the arc length from 0 to pi, and then multiply it by 2, okay? And then multiply it by 2. So we get 2 times the integral from 0 to pi, because what's the length above is the same as the length below. And again, we have f of theta squared, 1 plus cosine theta squared, plus negative sine theta squared, which is, I was just saying, the derivative of 1 plus cosine is 0 plus negative sine theta. So when you multiply this out, notice you're going to have a cosine squared plus a sine squared, which will reduce to 1. And it all reduces to 2 plus 2 cosine theta d theta. Okay? Well, 1 plus cosine theta is equal to 2 cosine squared. So if we take a 2 out of here, right, we get 1 plus cosine theta. 2 times 1 plus cosine theta. So we get 2 times 2 cosine squared theta over 2, which gives us this 4 cosine squared theta over 2. Well, the square root of 4 is 2, so we can pull that outside, and 2 times 2 is 4. And the square root of cosine squared is simply cosine. So we have a much simpler integral to solve, the cosine of theta over 2, which is simply the sine of theta, because we're taking the integral, not the derivative. It's not negative. Be careful there. The integral of positive cosine is positive sine of theta over 2. Now, of course, we had to do a substitution that u equals 1/2 theta. And since we don't have a 1/2 inside, if we add the 1/2 inside, we have to offset it by its reciprocal, which is 2 outside, which gives us the value of 8. And that's just doing your substitution for integration substitution. So we get the cosine of u du. All right. And then when you evaluate that between 0 and pi, you get the value of 8. Okay, I'm not going to walk through that calculation. So we've had a lecture here. It's right at an hour, and we only have one lecture left. So we're almost there, guys. Almost there.